when the size is tightly controlled, it can split into two distinct outputs at each node, right? So if one is alpha, the other is inevitably minus alpha. Hello everyone, this is ERA, the quantum chip technology announced by AWS. You know the existing quantum computer technologies? We need to explore how it stands apart from technologies like IonQ's ion trap or Microsoft's recently introduced Majorana, which I covered in a previous video. While AWS's method also uses superconducting technology, it takes a unique approach from the outset, differing from both traditional superconducting techniques and other quantum chip designs. Right from the outset, they adopted an approach that significantly minimizes the occurrence of errors. You see, the traditional superconducting method is known to generate a high number of errors, which has been a persistent issue in the field. For instance, Google recently released their Willow chip and discussed how they employed quantum error correction to address this problem. By using surface codes for error correction, errors can be fixed, allowing the number of qubits to be increased while ultimately reducing the number of errors. However, the CAT qubit proposed by AWS is fundamentally different from traditional qubits, as it operates on a different principle. This method using qubits can be designed to almost entirely prevent errors in specific parts. If this method is applied to the superconducting approach, the errors that used to occur frequently in the traditional method. I've been diving into this topic, wondering whether to make a video after fully understanding it. It's quite challenging and demanding, but if you can conceptually follow what I explain, you'll see how superconducting methods are evolving. You might find it worth exploring further. Also, since I've been collaborating with Guaido from Andescience for over a decade, even before the Andescience channel was created, I was deeply engaged in science communication. Leveraging my engineering background, I will now delve into the engineering aspects of this topic. The main point is that they utilized a new type of qubit which has never been attempted before. To grasp this concept, we need to understand what a qubit is. I apologize for explaining qubits in an oversimplified way repeatedly. Due to my limitations, many of you have created videos or left comments. Now let's discuss the qubit developed by AWS. To understand the new approach to qubits, what exactly is a traditional qubit? Let's briefly touch on this topic. You often hear that traditional computing, whether it's our computers or smartphones, is fundamentally about processing zeros and ones. If you break down the images or videos we see, they are all composed of a continuous sequence of zeros and ones. However, the quantum bit, or qubit, inherently differs in its fundamental nature. 0 and 1 are not fixed to just one state, but are somewhat superimposed, existing as both 0 and 1 simultaneously. Because of this unique characteristic, traditional computing, which implements 0, 1, 1, 0, 0, 1 separately and calculates by moving back and forth in memory, takes longer. However, with this superimposed state, by utilizing qubits in quantum computers, you can see here how they are uniquely represented as 0 and 1. By representing these two states as alpha and beta, it allows for simultaneous computation, which is why you hear claims about solving problems that would take millions of years in just 5 minutes. However, this qubit is expressed as either 0 or 1, and from this point onward, I'll cover something I have never explained before because this method always seemed so straightforward. Traditional quantum systems, whether it's the superconducting qubits from IBM and Google, the ion trap qubits from IonQ, or the latest Majorana qubits from Microsoft, all rely on distinctly representing the states of 0 and 1. These technologies fundamentally operate by clearly differentiating between the 0 and 1 states. It's not merely 0 and 1. Rather, they are depicted within bars and brackets as 0 and 1. When we talk about superconducting qubits, these qubits rely on what we refer to as energy levels. The most stable state is known as E1, followed by the next stable state E2. Additionally, there are states like E3, E4, and so forth within the physical system. The idea is to provide energy. By choosing the two most stable states, we achieve a high level of stability, which is often referred to as having a long coherence time. These states are less sensitive, making them easier to control. Other qubits are more sensitive and prone to noise. Therefore, we denote one state as 0 and the other as 1, both physically and mathematically. Additionally, by leveraging the energy states of these qubits, which are arranged in a donut-like configuration, we have successfully created quantum bits using these two orthogonal states. When we explore the principles behind traditional superconducting qubits, we come across the Josephson junction, which includes two superconducting elements on either side. A superconductor is placed on both sides with an insulating layer in between where electricity does not flow. If this layer is made very thin, the tunneling effect allows current to flow through. However, unlike the room temperature superconductors claimed by LK99, naturally occurring room temperature superconductors do not exist, so extreme cooling is necessary. The conventional superconducting approach involves creating superconductors at extremely low temperatures, down to a few millikelvin. This allows the two quantum states to be distinctly separated. However, any external noise or slight environmental changes can cause significant fluctuations, leading to the states switching from 0 to 1 and vice versa. When using the Josephson junction in a superconductor, 0 and 1 naturally emerge. To utilize these two, we don't use them directly. We say that 0 and 1 are orthogonal to each other, using these two quantized energy levels. Since they are orthogonal, we express this using complex numbers. This is quite complex, right? We learned this in middle school. Or was it high school? If there is an error, instead of this, you would use I to express it as a complex number. Engineering graduates might remember this, but most have forgotten. Just think of it as two independent numbers that don't affect each other. These are commonly represented on the x-axis and y-axis, where the x-axis represents the value corresponding to 0. You can understand that what appears on the y-axis is expressed as 1. In this superconducting approach, the 0 and 1 states are represented by two orthogonal states. However, the ion trap method is quite similar in that it involves controlling individual ions by confining them within an electromagnetic field and a vacuum. The electron configuration within the ion itself has distinct energy levels, which are among the various energy levels available. They specifically select two stable ones. Similar to the superconducting method we discussed earlier, these two levels are used to represent the binary states of 0 and 1. In Microsoft's Majorana mode, this concept is similarly applied, where an empty state indicates 0 and an occupied state signifies 1. Instead of utilizing two distinct energy levels to represent 0 and 1, AWS has adopted a novel approach. This is where things might start to get a bit perplexing. So, what exactly did Amazon Web Services, AWS, unveil? A groundbreaking innovation. AWS has introduced a groundbreaking quantum computing chip, claiming it can cut errors by up to 90%. They highlight that the architecture is inherently designed to prevent errors, and it utilizes superconducting technology. Additionally, they noted that this innovation is rapidly advancing quantum computing in practical applications. It's called an oscillator because it uses an oscillator. It's important to understand why it uses an oscillator. This is what is known as the cat qubit. I'll explain this architecture next time. This principle could be a groundbreaking method in superconducting technology, which is quite exciting. The cat qubit method it uses is inherently about 0, and the term 1, as mentioned earlier, is not used here. The cat qubit, which is being directly discussed, is said to be a highly efficient method in relation to error correction. As many of you who have studied quantum mechanics might know, the concept of the cat qubit originates from Schrödinger's cat, where the cat is considered to be both alive and dead until observed. When we observe it, we determine whether it is alive or dead, but until that moment of observation, it remains in a superposition of being both alive and dead. This principle is what the cat qubit is based on. On February 26th, an open access article was published in Nature, detailing hardware-efficient quantum error correction. Here, we have some proud Koreans like Mr. Kyung-Joo No and Mr. Man-Young Lee. I would love to meet them and learn from them. The cat qubit concept was already introduced in December 2013. That's over 10 years ago. A concept like this has emerged, and typically, when we represent a qubit, we use 0 and 1 as the two states. However, the cat qubit, instead of using 0 and 1, utilizes a specific value called alpha and its counterpart, negative alpha. These two values are used as axes, so the horizontal axis is originally represented by these values. So, instead of representing it along the y-axis as y, 0 and 1, they deliberately generate an oscillator to create an alpha axis and a minus alpha axis. This method makes them interact as if they were complex orthogonal to each other, which might be quite confusing, right? So, from the very beginning, you can't just arbitrarily decide to use alpha and minus alpha, and then claim, I'll use these two qubits for my calculations. It doesn't work that way. As I mentioned earlier, they selected the two most stable ones and named them 0 and 1, not just because they are stable, but because they maintain orthogonality. They specifically chose this approach, whether it is the ion trap method, the superconducting method, or other techniques, because these conventional methods require maintaining the orthogonal property of 0 and 1. But why is that necessary? So why do we need to choose between 0 and 1 when they are orthogonal, but suddenly we use alpha and minus alpha? Doesn't that raise questions? So I'm going to explain this step by step, but keep this in mind. What am I talking about? What exactly is a qubit? Rather than having 0 and 1 as separate entities, they are combined to coexist simultaneously, which is a key principle in quantum computing. To achieve this, the two states must be orthogonal, much like how a horizontal line and a vertical line intersect at a right angle. When observed, it must be distinctly identifiable as either 0 or 1, without any uncertainty. We need to design their qubits with the inherent properties they possess. Otherwise, they will remain in a superposition of both 0 and 1, making it difficult to determine their exact state. Even if we store information at the moment of measurement, it might get lost because quantum mechanics defines these properties based on the principle of orthogonality. They take advantage of these states that can be made orthogonal, which is a method also used in ion traps. Thus, the act of selecting states like 0 and 1 is crucial. Now you might be wondering why I'm suddenly talking about this and how one can choose between alpha and negative alpha. The thing is, alpha and negative alpha are not naturally orthogonal states. When the alpha value is increased more and more, it gradually reaches a state that is almost orthogonal, and at the same time, it creates a condition where errors are not likely to occur. This is the key point to understand. Instead of using the traditional 0 and 1 qubits, an oscillator was created with states represented by alpha and minus alpha. Initially, these states were not orthogonal, but by gradually increasing the alpha value, orthogonality was errors achieved. Consequently, the distance between alpha and minus alpha is significantly greater than that between 0 and 1. As the distance increases, it becomes challenging to determine if it's a 0 or a 1, but with this technology, it can clearly identify whether it's alpha or minus alpha, thereby reducing errors. Now, let me give you an analogy. Imagine a fountain with two separate streams of water and two holes. If the water streams are weak, they might merge and come out together. When the water pressure is really high, the streams can forcefully separate from each hole and come out as distinct jets. Wouldn't you agree? In this scenario, if one value is designated as alpha, then the other value will be distinctly marked as minus alpha, ensuring that the water on one side does not mix with the water on the other side. As the water pressure increases, the alpha values become more firmly fixed, originally set at 0 and 1, ensuring a clear and distinct separation between the two. Think of it as a physical energy gap between them. As we continue to increase the alpha value and the pressure, it ensures these states remain completely distinct. Does this help you visualize how we prevent any mixing between these states? Utilizing this approach, as you increase the alpha value and the water pressure, the state on one side mixes with the other state, leading to what we often call a bit flip error. This error occurs when a 0 turns into a 1 or a 1 turns into a 0 in a sudden and drastic manner. By significantly raising the alpha value, this state can be effectively implemented. In other words, when the alpha value is low, the streams mix together from the start, making it hard to distinguish between them, which indeed leads to errors. Initially, they weren't orthogonal, so like streams merging from a single source, they inevitably got mixed up. But as you keep increasing the alpha value, what happens then? Each axis is perfectly separated, much like the axis of 0 and 1, but with stronger amplitude, it can be much farther apart than the traditional 0 and 1, reducing the likelihood of errors. This approach is what we refer to as the cat qubit. In terms of complex numbers, the traditional axes of 0 and 1 are represented in this manner. By representing it along different axes of alpha and minus alpha, we can make them orthogonal, even though they are not originally orthogonal. To summarize, 0 and 1 are inherently orthogonal, and we send them in this state. The concept was to create a qubit by superimposing 0 and 1. However, with alpha and minus alpha, they are inherently not orthogonal. At first, instead of using superposition, if we compute the orthogonality of alpha and minus alpha, it can be represented in this manner. As alpha increases, since it is exponentially negative, it approaches 0. When alpha is a small value, it cannot satisfy orthogonality on its own, making it unusable. However, by employing an oscillator, alpha and, to implement minus alpha, we can increase the value of alpha itself, allowing us to extend it far beyond the limited physical distance between 0 and 1. This approach prevents the occurrence of bit flip errors by covering a much broader range. It's akin to NVIDIA's NVLink, which connects GPUs by enhancing the voltage level beyond standard limits. To support a much higher standard than PCI Express when communicating, they adjusted the voltage level slightly, instead of just sending 0 and 1. By dividing each section into 4 stages with -3 volts, -1 volt, 1 volt, and 3 volts, it becomes possible to send 2 bits per second instead of just a single 0 or 1. This method is known as PAM, and since it involves 4 levels, it is often referred to as PAM4 or 4PAM in the field of communication engineering. However, the reason complex numbers frequently come up in quantum computing discussions is that techniques like PAM4 utilize both the real and imaginary axes to form a two-dimensional system. This approach, called quadrature amplitude modulation, has been widely used in mobile communications since the 3rd generation era and continues to play a significant role in 5th generation technology. So, what's the advantage of expressing it in complex numbers instead of just sending 0 and 1? Normally, we could send one piece of information per second, but with this method, we can transmit 2 pieces at once by sending a single complex number. You can send 4 pieces of information, right? This allows you to send it in a much more compressed manner. However, instead of sending 4 pieces of information like 00011 in 1 second, how can we represent this complex number? Rather than sending x and y separately, we send the overall magnitude, which we commonly refer to as the amplitude. You can convert it into an angle and send it. Thus, complex numbers can be represented by amplitude and angle. However, the current KEQ method involves significantly increasing the value of r. By greatly enlarging the corresponding part of r, the system is designed to minimize errors caused by bit flip amplitude. On the other hand, the angle component, referred to as theta, is still commonly called phase in communication engineering, particularly in wireless communication. To adjust the amplitude, a separate pilot signal is sent, and this pilot signal is also used to calibrate the angle, commonly known as the phase, during the estimation process. In a similar manner, the CAT qubit initially did not have orthogonal components for what are referred to as alpha and minus alpha. By significantly boosting the alpha value and positioning the amplitude, known as r, much farther from the origin, they aim to reduce errors considerably. This method is deemed far superior to the conventional approach of using 0 and 1. So you can think of it this way for now. Now does the cat qubit have no issues at all? As I mentioned earlier, the amplitude part, which corresponds to the bit flip, can be effectively managed. Alright, from the outset, we can see that errors are minimal in this regard. However, when it comes to the angle phase, there are still quite a few errors. You could say we successfully split the stream into 2 two distinct streams, but it still gets affected by external factors like the wind. Although these states are still susceptible to disturbances and can cause errors, reducing the bit flip error in superconducting methods can have a significant impact. To create these cat qubits, the alpha and minus alpha states I mentioned earlier need to be implemented as oscillators and maintained stably, which requires precise control and stability. Managing this process demands extremely precise engineering, but AWS has actually managed to create this. Moreover, as the number of qubits grows exponentially, it becomes crucial to ensure that these oscillators are properly synchronized to function accurately and represent the states of alpha and minus alpha. The challenge of physically synchronizing different oscillators remains, but achieving the implementation of the previously introduced cat qubit approach is indeed a significant milestone. Actually, because I am trying to explain things while omitting a lot of details, my ability to explain might not be as easy as it seems. I hope those smarter than me can add more details. Ultimately, using this cat qubit, we have created a structure with far fewer bit flip errors than traditional superconducting methods. Superconducting methods are not stagnant. They explore quantum error correction and approaches that inherently prevent errors. This is why the AWS Ocelot chip, based on an oscillator, is well suited for this purpose. This design has significantly reduced the probability of error